The easiest way to start an argument in an online audio group is to claim that all wires sound the same, or that all wires sound different. Nothing polarizes audiophiles, and even some audio professionals, more than challenging their beliefs. For hi-fi enthusiasts, wire beliefs are among the most strongly held. Audio engineers will tell you that it's simple to measure wires to learn how they affect the audio passing through them. The electrical properties of wire have been understood fully for more than a century, and audio engineers know exactly what to measure. But some people believe there's more to audio than test equipment can measure, and prefer to trust their ears. As a professional audio engineer with more than 50 years' experience both recording and performing music, as well as designing electronic circuits such as this mixing board and half the equipment in the outboard rack at right, I'm certain that measurements tell us all we need to know about any device, including wire. But you have to measure everything, and that's not a simple task for electronic devices such as preamps and equalizers. However, wire is simple to measure because wire can't add noise. Wire can't create distortion either, unless a connector is badly tarnished or soldered poorly. The only thing wire can affect is overall volume level and frequency response due to its resistance, capacitance, and inductance. If you measure two wires using these standard metrics to prove they sound the same, someone will insist there's more that affects the sound of a wire. That's not true, but many people believe it. They might insist that some wires sound better because they're made from oxygen-free copper, or because they employ a special type of insulation, or because they're built from many individually insulated copper strands. Of course, if any of that was true, it would show up in the standard audio measurements. Confusion about wires is so common that in 2017 I wrote an article for Sound on Sound magazine to explain the properties of wire, and I link to it often in audio groups. But inevitably, someone will object and say I can't know for certain that wire doesn't possess more than the known properties of resistance, capacitance, and inductance. Fortunately, there's an absolute and totally foolproof way to assess how any wire affects the sound passing through it. In 2013, I gave a presentation to the Audio Engineering Society explaining how audio devices are spec'd and measured. One of the concepts I explained in my AES workshop is the value of the null test. A null test subtracts one signal from another to identify all differences between two signals, including things you might not think to measure or even know about. So for those who believe there might be more to audio fidelity than standard measurements show, a null test removes all doubt. The beauty of the null test is that it's absolute and reveals all differences, including frequency response, noise, distortion, phase shift, and every possible artifact, whether known or unknown. To subtract one audio stream from another, you simply reverse the polarity of one signal, then mix them both together. Whatever remains is the difference. This point is very important because it dispels the common beliefs that science doesn't know everything people can hear, or that some aspects of audio fidelity can't be measured using sine waves and other typical test signals. Nulling has been around since the 1940s, so if there really was more to audio quality than the standard known metrics, it would have been revealed long ago. If you use a blind test to prove to someone that they can't hear a difference between two wires, they might complain that blind listening tests are somehow flawed and can't be trusted. That's not true either, but again, many people believe this. So the value of null testing is that it's absolute and reveals all differences between two wires or other devices. Any difference between the two audio signals is revealed in the null residual. This is the audio that remains after subtracting one input signal from the other. This residual audio reveals the size and makeup of the difference. In other words, what you are hearing is the difference between the two signals. So if the residual is 90 dB softer than the input sources, you're assured that nobody can possibly hear it while the music plays. Further, no two wires will ever measure exactly the same. One length of speaker wire might have a resistance of 0.07 ohms and another 0.071 ohms, which is insignificant when driving an 8-ohm voice coil. In this case, the volume difference is 1/1000th of a decibel, which can't possibly be heard by even the most gifted listener. A null test lets us isolate and amplify any tiny difference enough to be heard clearly and also measured. So again, a null test reveals the difference between two signals instead of measuring the wires directly. This way nobody can complain that we might be missing something audible that matters. A digital null test using audio software is pretty simple to do. For example, some people believe that music files can sound different when played from different hard drives, and this is a perfect application of the null test. For a digital null test, you simply put the same music file on two different hard drives. Then bring those files into separate tracks of the audio software with the polarity of one track reversed. The polarity reversal cancels anything common to both tracks, so when the music plays, any difference between the audio data streaming off the hard drives will be apparent. If the result is silence, as shown here at the bottom output meter, then the audio streaming off both hard drives is identical. In my other AES video, Audio Myths, I used digital nulling to verify the mixing accuracy of audio recording software and to prove that audio software and plugins don't have a sweet spot volume level at which they sound better, among other common myths. However, analog null testing is much more difficult because even the best analog circuits add a tiny amount of noise and distortion of their own. So it's important to ensure that the testing device itself doesn't corrupt the process. Keeping the input signal paths as clean as possible was my main challenge when designing the null tester shown here. I used very high-quality parts and made the layout as small as I could by using mostly tiny surface-mounted op-amps and other components on a 4-layer PC board. 4-layer boards include ground plane and power layers inside the board, providing extra isolation between the top and bottom circuits when needed. The input stages use the latest state-of-the-art OPA 1612 op-amp that has extremely low noise and distortion so low it requires special instrumentation to measure. Making all the cutouts and holes in the metal case was a lot of work because all the holes have to line up precisely with the related controls on the PC board. Thanks to my friend, master craftsman Phil Kramer, who did this work. Besides keeping noise and distortion as low as possible, successful nulling also requires the input signals to have precisely the same volume, timing, and phase. If the phase differs by even 0.005 of a degree, the null is limited to only 80 dB or less. Again, the null tester avoids potential objections to standard measurements because it doesn't actually measure anything other than the volume of the null residual. Rather, it extracts the difference as an audio signal that can be measured, recorded, analyzed in detail using FFT software, and even heard through a loudspeaker or earphones. Just as modern distortion specs combine total harmonic distortion plus noise, the null tester isolates the sum of all artifacts as a residual difference, which you can then measure and hear by itself to assess its audibility. If two signals can be nulled to silence or near silence, then they are mathematically and audibly identical. Period. End of story. The null tester sends the same signal through two paths, then subtracts one signal from the other electronically. If the signals are identical, the result is silence. The block diagram at top shows the concept based on polarity reversal and summing, with the actual circuit schematic below. One important use for the null tester is comparing a $3 RCA wire to a $1,000 RCA wire, or comparing a wire resting on the floor with the same model wire raised up on elevators, or taking a wire that has a signal flow arrow and connecting it both ways to see if reversing the direction really makes a difference. So if some vendor claims his wire sounds better than normal wires in ways audio engineers don't consider, the difference between his wire and a normal wire can be isolated, then easily examined and understood. If the null residual is silent, or at least 80 dB down, you know for certain that the vendor is either lying or incompetent. Some expensive wires have a mystery lump in the middle that might contain passive components, such as diodes or resistors, or the lump might contain nothing at all. A null test will reveal that too, without having to break open the casing. Most modern audio devices have a low output impedance and a high input impedance. This method is called bridging, and it has many advantages over the older method that matched the input and output impedance. typically 600 ohms based on early telephone systems. Most devices today have an output impedance of 100 ohms or less, with an input impedance of 10,000 ohms or more. The SanDisk Clip Jam media player I'm using as a source for both test tones and music can accommodate 24-bit WAV files for very low distortion, and its headphone jack has an output impedance of about 7 ohms. However, any reasonable signal generator, media player, or other audio source may be used with the Null Tester. The Null Tester has an input impedance of 10K, which is typical for line-level audio devices. But the Null Tester also features a variable output impedance, up to 1,000 ohms, because a higher output impedance can increase high-frequency losses due to wire capacitance. So this lets us test for a possible audio difference between wires when they're connected to tube equipment, for example. The external output driver unit accepts a mono input and sends that through all 6 output jacks at once. This allows comparing different wire types, such as an RCA wire versus an XLR microphone cable. Here again you can see both the block diagram and an actual schematic, though the schematic shows only the output driver. The audio input is split into 2 paths, then sent through a dual potentiometer, then through the wires being compared, and finally into the Null Tester. It's important to point out that a wire between a turntable and its preamp has additional considerations. If a wire has a little more capacitance than usual, it will probably pass audio well enough between competent line-level devices. But phono cartridges require a specific capacitive load, so different wires really can affect the sound. Again, all differences are revealed in the null residual, including timing, distortion, phase shift, response errors, noise, and anything else that might exist. As you can see in this table, the Null Tester can identify signal differences smaller than 1/10,000th of a decibel. This is far greater resolution than any conventional audio test can measure. Fourier proved years ago that all sound is made up of sine waves, but some people don't believe that either. So another advantage of the Null Tester is that it works just as well with music for the signal source as sine waves. Full-range music provides many frequencies at once, rather than one frequency at a time using 1 kHz or 100 Hz sine waves. Whether comparing boring test tones or high-energy rock music, the Null Tester can reveal artifacts or other differences softer than -110 dB. The test is based on relative differences, so it works independent of the source material. When considering artifacts such as distortion, this table relates the measured residual volume to an equivalent amount of distortion. When comparing wires, the null residual will likely be 60 dB or more below the input signals, depending on each wire's capacitance and other factors. So the Null Tester raises the gain after nulling by as much as 80 dB, and the built-in output amplifier can increase that to a maximum total of 114 dB. The Null Tester comprises 3 boxes: the tester itself, a power supply, and the output driver box with 3 parallel connector pairs. Since the Null Tester provides up to 114 dB total gain, I kept the power supply separate to avoid supply noise or other interference getting into the tester and being amplified along with the null residual. Dialing in the deepest null possible requires great precision, so the null potentiometer at left is a 10-turn type. As explained earlier, null residuals are extremely soft, often just a few microvolts, so the makeup gain switch amplifies the signal in 10 dB steps, up to a maximum of 80 dB. The VU meter is readable over the top 20 dB of its range, so a total null depth up to 100 dB can be measured with reasonable accuracy. An external meter or oscilloscope can offer even greater precision when needed. The meter monitor switch sends either input 1, input 2, or the amplified null residual to the output stage for listening or recording and for watching on the meter. So first you'll select either input and adjust the source volume to read 0 on the meter. Then when you switch to null, the gain switch setting and the VU meter together tell how much softer the null residual is compared to the input. The difference between most wires is so small that the null residual can be even more than 100 dB down. The built-in 2-watt output amplifier can drive headphones or a small loudspeaker, and it offers up to 34 dB of additional gain. So you can connect an external meter or oscilloscope to the headphone jack in front, or to one of the line output jacks in the rear. That's what I did for my wire comparisons. A production version of the Null Tester will likely offer even more gain to allow metering nulls as deep as minus 110 dB directly. This graph shows the frequency response of the tester for the input channels and also for the null residual at 50 and 80 dB of gain. This shows frequencies only up to 100 kHz, though I measured to 150 kHz and the input channels were still less than 3 dB down. The high frequency fall-off at plus 50 and plus 80 in the null stage is from a simple filter I added after the tester was built. I wanted to remove ultrasonic frequencies from the tester's own noise, since that limits the maximum measured null depth. A production version will have proper band limiting that's flat to just past 20 kHz, then rolls off sharply at 24 dB per octave. I'll probably include an option for A weighting as well, and I'll fix the slight low-frequency roll-off so it's flat down to 10 Hz. I used to have a beautiful audio-video studio in the upstairs of my house. But now most of it has been turned into an electronics shop. These are parts bins for the various Null Tester versions I developed, plus a few other recent projects. This was my first attempt at a Null Tester, but it was too large and tried to do too much, and it couldn't be manufactured efficiently enough to sell for a reasonable price. I built the parametric equalizer in the 1970s, and an article describing the circuit is on my website. The Mojo Maestro was for a more recent article in Audio Express magazine, and the Null 2 box is a prototype for the Null Tester featured in this video. This shows the prototype's construction built onto a generic perforated circuit board using traditional parts rather than tiny surface-mounted components. Including the earlier fancy version, I've so far spent a little more than $3,000 developing this device. I have even more electronic parts in other boxes not shown here. I keep some of my cats in these boxes too. Whether or not this becomes a commercial product, I had a lot of fun doing this over the past 2 years, and I learned a lot. I have only limited desk space at my computer, so I bought this LabNation USB oscilloscope that also includes a signal generator and logic analyzer. It's really great, and you'll see it in action during the live portion of this video coming up shortly. As you can see, I have just enough room for the tester and the scope, plus a few audio adapters. When I need to solder parts onto the PC board, or even just to solder connectors onto a wire, I have to go downstairs and work on the kitchen counter. Here, I'm making my own wire to feed the Null Tester's output driver from my media player. I used high-quality Mogami W2314 wire that has extra low handling noise. This prevents such noise from corrupting the test signal and avoids objections that a normal wire might mask detail that could possibly have revealed a difference in the wires being compared. Okay, so now we get to the live portion of the Null Tester demo. Earlier today, I measured the capacitance of many of the wires that we're going to compare, the RCA wires. I have this multimeter that can measure capacitance, and there's a little adapter cable I put together. But of course, there's some capacitance on this wire here before we get to the adapter. So I measured that. It was 243 puff, I believe, 0.243 nanofarads. First, I tested this cheap 3-foot black wire I've had laying around for years. This measures 292 puff, so minus the residual 243 puff, the wire has 49 puff, or 16 puff per foot. This is very good for any wire. Next, I tested this cheap gray wire, which was twice as high at 32 puff per foot. Still not bad, and more or less typical. Years ago, my cable TV company gave me a 5-pair RCA wire for component video plus stereo audio, which I separated for stereo only. This wire is 12 feet long, so it comes in at 62 puff per foot. Finally, I measured the Harmonic Tech Magic Link 1, which turned out to have the highest capacitance at 94 puff per foot. When we compare that wire to the others, we'll find out if the high capacitance has any effect. I have this arranged so that if you plug in only to input 1 on the quarter-inch inputs, I'm using switching jacks, it sends the same signal to both inputs. And this is a way that we can test the tester itself to make sure that we get a complete null, and all there is silence, or in this case, of course, it will be hiss. There's 100 and something dB of gain possible, of makeup gain, so there will be some hiss, residual hiss. But there will be only that and no signal leaking through. So we can start with a test tone. And you can see that this comes to exactly 0 on the VU meter. Then we can switch to the null. I much prefer 400 hertz to 1 kilohertz. It's much less irritating. So now we have the null, and now we're going to bring up the gain. It's already set to 40 dB, but the null has been calibrated pretty well here. Now there's 80 dB again. We turn up the volume so you can hear it. You can hear mostly hiss, and there's a little bit of coming through, but now we hit the null knob. All right, now to actually test the wires, I have to insert this little dummy to break the switch. Otherwise, the same signal is going to go to both, which isn't going to compare the two wires. So I'm going to plug this dummy into the back. So as I raise up the gain, you can see that the meter is still minus 20. So with 80 dB of gain, the null is more than 100 dB down. As I mentioned in the earlier part of the video, a lot of people don't believe that sine waves are a good way to test. Oh, well, it's not the same as music. And of course, it is. Music is sine waves. But we'll use music anyway. I have this media player here. And I should show you, this is kind of off the screen, but this is the output box that takes the input signal from my media player through the custom wire I made, and sends it out through all of these output jacks at the same time. I have it on a separate chair. One of the problems is the wires kind of coil around as they're being tested, and that makes them act as antennas. We're right next to a powered loudspeaker here, and monitors and the power supply. These have power supply. There's a computer right there. So when the wires are coiled, one or more wires may pick up hum, and we may hear that. And then you have to move the wires so that the hum pick up. And again, all it takes is a microvolt, 3 microvolts, 5 microvolts of hum to get into one wire. You'd never ever hear that, but that's all it takes to upset the null, and then the hum gets amplified by 100 dB. But anyway, so we'll use this music player. And I'm sorry that it's out of sight. I have it on a piano stool here that I can pull forward and back to accommodate different length wires. So first I'm going to compare this cheap black wire and this cheap gray wire. These are the ones that have the lowest capacitance. And we'll just use one channel of each, obviously. So we'll come out of there and go into input 1 of the Null Tester. Then we'll take this wire. And go into input 2 of the tester. Now I'm using music for this. So let's play some music here. And this is coming out of this little speaker here. So listening to either input 1 or input 2, that was listening to the black wire. And that's listening to the gray wire. And then in the middle we're hearing the null. Then we can turn it way up. And all there is hiss. So these wires are passing audio exactly the same. Let's try now this cheap black wire to my 12-foot long wire that I got from the cable company. And this has a lot more capacitance, and there'll be some difference in time delay, nanoseconds, picoseconds. And let me turn this way up. And you can hear the hum coming and going. That's what I was talking about. But the wires are the same. This is just picking up stuff from the computer. And that's why I wanted to be able to put it away on the bench that's just out of sight here. So now let's play the music again. And we'll listen to the different inputs. Input 1 and input 2. So each of those is one of the wires, and then we bring up the gain on the null tester. And again, we're able to get it the null to silence. And if you look at the VU meter, again, that's all the way down below minus 20. So that means this is more than 100 dB down. All right. And the noise of this device is about minus 110, which is about as good as you can get without like really special circuitry and a lot of really fancy stuff. Now this is the Harmonic Tech Magic Link 1 that Tim Stevens was nice enough to send me for a test. This costs $750, I think, $700, something like that. And it's as fat as a garden hose, and it has more capacitance than twice as much as any of the others, the short ones. So let's see how this compares and if this passes. Now this has an arrow, so I'm gonna have the audio go in the direction of the arrow, out of this and then into the tester. And this is so fat, I'm going to have to turn the tester around a little bit here. Now again, I don't know if you could hear the hum. When the wires, I don't think either wire is really picking up more hum than the other. When the wires are in the same physical place, they'll pick up whatever from the computer and all the interference in this room. But when they're in different places, they pick up different amounts of hum, so it doesn't cancel. So anyways, turn the volume down, listen to input 1 again and 2, just to confirm both wires are connected. All right, and then we bring the null gain way up. And again, we're able to null it to silence. And the reason I have to keep changing this is there's a little tiny bit of heat in the box. This thing is so incredibly sensitive that as the temperature rises, and this has already been on for about an hour before I started this video, but as the temperature rises and falls, tiny, tiny, tiny changes in the components make the null, this unbelievably critical null balance, shift just a little. So, just in a couple of minutes it takes to change to another wire, I have to change the null pot a little bit. All right. And that's just noise on the screen. All right, so now let's change the direction of the arrow. Let's hook up this wire backwards and see if that makes any difference. What do you think is going to happen? So now let's start the playback here. So both wires are working, and can we get a null? Yes, we can. I think it's safe to say that the wire marking, on this wire anyway, is pure bullshit. So what have we learned from this? Well, we've learned that of all the wires I tested, they all pass audio exactly the same. No matter what the vendor tells you, that this one has more clarity or more sparkle or more presence or more realism or better imaging or more solid bass, you could be sure that it's all pure bullshit. Bullshit. Because these wires are all passing audio the same, and when you reverse the polarity and add them together, the result is silence down into the hiss of the low noise preamps in this box. Now, I really wanted to get some, $2,000, $5,000 wires. Somebody told me there's a wire that costs $22,000 for an RCA wire, a couple of meters long. And I would have loved to get that. I asked in like 4 different Facebook groups, and I asked a dealer of high-end stuff who I know is a friend of mine, and I asked somebody else who's actually science-minded. Nobody was willing to give me anything. Nobody in any of the audio groups. In fact, I got kicked out of one of them, and I had a bunch of my posts deleted in the other. As it went on, people would ask questions, well, how does this work? So I said, well, it subtracts the 2, and it's really high-quality precision parts on a 4-layer PC board. And, all this stuff, it was really calm and rational, and explained it, and showed, photos of stuff. And in the end, it was just a big flame fest. And because if you spent $2,000 on wiring, some jerk like me comes along and says, well, you wasted your money. That wire is no better than the $3 wire that comes for free with your CD player. Of course you're going to be mad. You'd be mad at yourself is what you ought to be. So anyways, I hope this demo has been compelling. I hope that it's clear how this thing works and why this proves that these wires are passing audio exactly the same. Thanks a lot for watching.